All right, everybody, we are in the home stretch. We just have 4 chapters left. And each of these chapters, though, is a 1-week chapter. So you'll have review questions due every week for the next 4 weeks. And each exam, there'll be 2 more exams, and each exam will be over 2 chapters each. That being said, I'm going to shorten what is required for you to know for each chapter so that it is a reasonable amount, and I'll tell you which parts of the book that you can skip. Okay, so for this chapter, we're going to cover thermal preservation. And thermal preservation is the changing of the temperature or the heat energy is of a food to increase its shelf life. There are 2 forms of thermal preservation because this is just changing of temperature, right? So it can be both heating or cooling. So with heat processing, we're going to be transferring heat energy into a food, and that does have the potential, and in fact, usually the goal, often the goal, to destroy enzymes and bacteria. And one key thing about the heat processing is that it does require packaging to prevent recontamination. Okay, so you cook a roast at home and it can easily be recontaminated because it is not put into a clean package afterwards, and or you touch it right after you've cooked it. Okay, and so there are food safety concerns with that, and we got to make sure we get it cool in enough time, and there is a shelf life limitation to it once it's in your refrigerator after you've cooked this roast at home. Whereas things that are made in the food industry, that packaging usually is designed to give those foods a longer shelf life. Okay. And as well as the heat preservation techniques that have been used. Okay, then the other part of thermal preservation is cold processing, and that is pulling the heat energy from foods, and that's not going to destroy enzymes and bacteria most of the time, but it will slow that molecular movement and prolong shelf life. Now, we are going to focus this week on just the heat processing part of this, and the cold processing. If you're interested, you can just read that part of the chapter on your own. There are some interesting things in there, like why do bananas turn brown in the refrigerator? Tells you why. And there's some interesting things to understand about uh, freezing methods and how fast you freeze and thaw things and how that affects food quality. But uh, for the purposes of our class and being able to cover what we need to in this chapter in just 1 week, and it not be too overwhelming for you, we're just going to focus on the heat processing. And there's going to be a little bit of something else that I've added extra at the end that isn't actually thermal preservation, but it's related to a lot of the topics that we're discussing. Okay, so degrees of preservation when we're talking about thermal preservation. Okay, we have blanching, pasteurization, commercial sterilization, and sterilization. We're going to go through each of those. So blanching, we've talked about blanching before, so you know what it is, right? We have that food in boiling water or steam for a very short period of time. It's immediately plunged into a cool water bath afterwards to stop that cooking because we only want that heat to be applied for a very short period. The reason we do that is not for any microbial purpose, but it's only to denature enzymes, typically when we're preparing those foods before freezing so that we don't get discoloration and things in the frozen foods. It can also be used to loosen skin in some fruits and vegetables. If you recall, I did that back when we had a lab where we had tomatoes and we needed to take the skin off of them. I blanched those tomatoes prior to us peeling the skin, and it made them easier to peel. So the second level of heat processing is pasteurization. And this is considered low heat compared to other heat that we can apply. And the pure design for pasteurization is focusing on the pathogenic microorganisms. It will also stop enzyme activity. So sometimes that pasteurization, the enzyme activity is the focus, but most often it is destroying the pathogenic microorganisms. Now, any spoilage organisms that also get destroyed, that's a bonus, okay? But the main focus of pasteurization is destroying pathogenic microorganisms, okay? The temperature and time that are used during this pasteurization process are calculated based on the specific food and what pathogens or enzymes we're trying to target. Okay, so some pathogens need a higher pasteurization temperature than others. Some foods may need a higher pasteurization temperature than others, and we'll get to why that is in a minute. So foods that are pasteurized for specifically controlling enzyme activity would be beer, wine, and fruit juices. You don't want, like beer and wine, you don't want to keep fermenting those once you've reached the end point. And so you want to stop the enzymes in the yeast that control that fermentation process, okay? Fruit juices have enzymes that can cause browning. We don't want brown fruit juice, so we want to stop those enzymes, and so those will be pasteurized. Now, fruit juices, there's also a pathogen concern too, and so it's actually kind of dual. Now, foods that are very commonly pasteurized to kill pathogens, we obviously know about milk, raw oysters, eggs sometimes, right? Most of our shell eggs are not pasteurized, but they can actually be pasteurized in the shell and be more safe for making products that include raw eggs, like hollandaise sauce, for example, or mayonnaise. Now, more commonly, if you buy liquid egg product in the store, that has been pasteurized also. Raw oysters, so both of these, for the raw oysters and the eggs, you're applying just enough heat to kill those pathogens and trying not to affect the consistency of that actual product. Because we know with eggs, if you heat that to too high of a temperature, and the same with oysters, they're going to firm up and not be at all the same texture as they were when they were raw. Okay, and that is the good thing about pasteurization, is you can use a fairly low heat treatment that's just enough to kill the pathogens without affecting the texture too much. You're still going to have some effects on texture, as well as potentially some other things that you might prefer not to affect. So quality will be changed when you pasteurize. Okay, and so the third level of heat processing is commercial sterilization. Okay, this is going to be a high heat treatment that is designed to kill not only all the pathogens, but also all the spoilage organisms that are relevant to that product. Now, this commercial sterilization is not 100% sterilized. It has not killed, or is not guaranteed to kill, all of the organisms that are possibly in that product. Now, it's going to kill all the vegetative cells, but it might still contain spores, which are bacterial cells that have this resistant shell that makes them able to survive some extreme environments. Now, the key thing here is, in general, this is the spores that may still be there do not include Clostridia. So the Clostridium perfringens, but more specifically Clostridium botulinum, we are targeting that one. All right, so in commercial sterilization, there's definitely enough heat treatment to kill that one, because especially in our low acid foods, that one is our biggest concern in canned foods, and we are definitely trying to kill that spore. But there may be other spores that are more resistant to heat that would not be destroyed with commercial sterilization. Okay, so each of these, we are just upping the game a little bit. Okay, blanching, we're just destroying some enzymes. Pasteurization, we are focusing on killing pathogens. Commercial sterilization, we're focusing on killing any bacteria that would cause a change in our food, whether that is pathogenicity or spoilage. Okay, so it would make that food unsafe or uh, or something that you would not want to eat. Okay, so this is what is used for our canned foods that we buy in the store. Okay. Now, this sterilization process will make it so, because we've killed everything that can grow. These spores that are not killed, they're going to remain spores because unlike Clostridium botulinum, they probably are aerobic. And so you have them in a canned environment, which is more anaerobic. And so it's in an environment that it cannot um, sporulate and go into the vegetative state and start growing and cause spoilage. Okay. Um, so most canned and bottled foods that will keep with good quality for 2 or more years. After that, generally those foods are still safe because again, we've killed everything. We've definitely killed all the pathogens and we've killed all the spoilage organisms also. And so they're still safe, but they may lose flavor and texture. So generally on those canned foods, you're going to see like more of a best by date, not a sell by or use by date. And that wording is kind of important. And that means just for the best quality, it needs to be eaten by that date. And what happens afterwards is just chemical processes that will for sure happen over time that eventually degrade the product to a point where the quality is not good anymore. All right, so then our fourth and final level of heat processing is sterilization. And so this is going to be high heat and it's going to result in complete destruction of all of the microorganisms. Sorry. Okay, sorry if you could hear that. My dog coming in here panting very loudly. I paused it to get him out of here. Okay. So this high heat treatment is going to result in complete destruction of all the microorganisms. Okay. So again, upping the level here with sterilization, we're at 100% gone. Okay. To achieve this, all parts of the food must reach 121 degrees Celsius for 15 minutes. This requires a moist heat because the heat penetrates the food as well as the microorganisms better if it's going through water. Okay. The time required actually to get to this point depends on the size, the density, all the other qualities of that food. And so mostly sterilization, it's easiest to obtain in liquid or pureed foods. And it's not only for that time requirement, but also because of quality. So in general, in the food industry, and we'll get to this towards the end too, is we want to have the lowest possible level of these heat treatments that preserves the quality. Well, first maintains safety, gets us to safety, then maintaining the quality attributes, and finally low cost. And so it's a balance of all of these things. And so because of that, the sterilization process is really just used in liquid or pureed food because you think about super high moist heat, it is going to very much degrade foods and you're going to end up in some foods with mush if you apply this process. And so it cannot be used in some foods at all. So what affects what heat processing method that we choose, kind of separate from what I just talked about. We're going to go through the four main variables that affect our heat processing method. Okay, and keeping in mind that Heat processing is going to cause changes in texture of foods. Okay, the higher the heat, the more mush, softer your food gets. It's going to cause changes in color, browning in fruits and vegetables, for example, and it will cause change in nutritive value because we know that some of our vitamins and minerals are susceptible to heat and lose their effectiveness if they are heated. Okay, and so we should use the heat processing method that balances the best that we can, that safety and shelf life, how long that food will last, as well as the preservation of those original qualities of the food. And so our 4 factors to consider that we're going to go through in more depth are heat transfer, time versus temperature, food components, and the pH of the food. So heat transfer. There are 2 main methods of heat transfer that are going to be occurring in our specifically commercial sterilization is what we're going to be focusing on right now. So the first method is conduction. And so this is where the heat is transferred from the outside of the can. You have heat coming in on all sides of the can because that can is going to be submerged in water. And so through molecular collisions, it will just slowly migrate to the most inner part of the can. The more viscous, the thicker the food, the slower that heat transfer is going to be. And as you can imagine, because it is just purely based on coming through the size of the can, the size and the shape of that can are going to be important. The common foods that use purely conduction or mostly conduction for their heat transfer when they're canned would be corned beef hash, pumpkin pie filling, tomato paste. These are things that have a limited amount of liquid that is able to move in the can, and they're just denser products, and so the conduction is the only way that the heat will transfer through the can. The cold spot in these cans that are using primarily conduction as their heat transfer method is going to be in the geometric center of that can. And the cold spot is going to be the part in the can that is the last to heat all the way through to where it is at a safe level. So then convection, and we've talked about these heat transfer methods before. With convection, there's liquid that is in the can that when it is heated, it will then move to the top of the can, and you get currents that develop, and that is distributing the heat through the can. It's going to distribute that heat faster, so it is a more efficient method of energy transfer and raising the temperature than conduction. So common foods that use primarily convection when they are being preserved with heat would be chicken broth or juice, right? The more liquid, the more it is relying on convection because that liquid doesn't have any barriers to that movement. So the coldest spot in a convection system in the can is going to be just below the center of the can. And then if we have a combination of foods, so we have liquids and solids in the foods, then we're going to have a combination of conduction and convection, right? You have the chunks of food that are dispersed in the liquid, and there's the liquid is having convection going on, but the chunks of food, when the heat is reaching the outside of that, it still has to use conduction to get to the middle of those chunks of food. So common foods like that would experience this process would be fruit cocktail, soups with large particles, canned vegetables, anything that has chunks of food in it as well as liquid. And just like with convection, I just used the same same image here, the cold spot in these is going to be just below the center of the can. And it's important to know where that cold spot is, because when they are validating these processes to make sure that the time temperature combination that they use in that canned good is achieving the commercial sterilization that they want, they will insert thermometers into the can, and they want to make sure that that thermometer is located in the right spot, in where that cold spot would be, to make sure that that coldest part of the can is going to be getting to the temperature that it needs to get to. So the second factor to consider is time versus temperature. Okay. And in the book, it talks about a thermal death curve. And these thermal death curves are actually graphs that are used to determine the cooking time and temperature to kill a specific organism. And so this is an example of one of those graphs. And it tells you at one specific temperature. Okay, this is the x-axis. X-axis is the time in minutes, and the y-axis is the number of surviving cells. Now, it's called a curve. Why isn't this curved? Well, this is in a log scale. So one log would be 10 microorganisms. 2 logs would be 10 to the 2, which would be 100 microorganisms. 3 logs, 10 to the 3, 1,000 microorganisms. 4 logs, 10 to the 4th, 10,000 microorganisms. 100,000 microorganisms, 1 million microorganisms. Okay, so if we were to plot this in a linear scale instead of a log scale, that it would look like a curve. It would kind of look like this. It would be an asymptotic curve. Okay, so and so how this chart or the table in the book was developed was multiples of these. Okay, so this table has 1, 2, 3, 4, 5, 6, 8 temperatures. So there would be 8 different graphs that someone has measured what the decrease in surviving cells was at that specific temperature over time. And then they combine that all into a more easy, straightforward table that you can look at and say, okay, so at this temperature, I need this amount of time to kill a certain level of bacteria. And there's usually a certain log reduction that you're looking for. So if I need a 10 log reduction, then I would look for that on not on this particular graph, but I would look for that on this graph and think, okay, that is the time temperature combination I need for that temperature. If I only needed a 2 log reduction, then I would find it right there on the graph, right? So the essential thing with the time versus temperature consideration is that fast, high heat causes less damage to the food, not the microorganism, but the food, than a prolonged time at lower temperatures. Okay, and so this example from the book was Clostridium botulinum control at different temperatures. And so at 100 degrees Celsius, which is just boiling, we would require, and this is for the specific food too, it's going to vary per the food, but for this food, I think the book said it was green beans, if I'm not mistaken, 330 minutes of boiling to control these Clostridium botulinum spores. Okay, so that is 5.5 hours of boiling your green beans. They will definitely turn to mush if you do that, right? Versus if we can get that product to 127 degrees Celsius with pressure, I only have to keep it at that temperature for a little over 45 seconds. Okay, probably like 46 or 47 seconds. And that would destroy those Clostridium botulinum spores. Okay, so even though that heat is super high, it is definitely not going to damage that food as much as cooking it at boiling temperatures for 5.5 hours. Okay, and so once again, we're balancing safety. We're going to achieve a safe cooking time temperature combination no matter what, but how can we balance the safety and maintain our quality and do it in a cost-effective way? All right. In some cases, this might not be the most cost-effective way. Maybe I get it just to 124 and I sacrifice just a little bit of loss of quality to reduce costs. Okay. Okay, and the third factor to consider are our food components. So there's two subset things to consider with this. One is, what are the microorganisms in that food? Okay, different foods have different organisms that we have to consider, right? A low acid food, we have to control Clostridium botulinum, whereas a high acid food, which is actually on a couple slides, we don't have to worry about Clostridium botulinum. But in chicken, we have to worry about salmonella. In green beans, not so much. And so our focus is on the pathogens of concern for that food. Okay. And the temperatures will be different depending on what organisms that we are targeting. Another food component to consider, there's actually four. So microorganisms, ingredients, and the other two will be on the next slide. So the second food component that we need to consider are what the ingredients are. And that's because some ingredients will provide a protective effect for microorganisms. And these include sugars, starches, proteins, fats, and oils. So the more complex the food is, essentially, the more protective it can be of the microorganisms. And it's something that can be overcome, but you just have to possibly increase the temperature at which you are preserving those foods, or increase the time a little bit to take into account that protective effect. And so research is done on every single kind of food to make sure that that time temperature combination is precise for what that food is to kill the pathogens of concern. In addition, some ingredients actually slow the conduction process. So it slows the rate at which the heat gets through the product and cooks it or gets it to the correct temperature all the way in the middle of that product. And so you'll have to take that into account, that you are going to have to cook for a longer time to get that desired temperature in the middle of the product because of that slower conduction. And specifically, the ingredient that slows that conduction process the most is going to be fat. Okay, and so fat is going to be really both, right? It's very protective and it slows that conduction process. Fat is an insulator. It keeps whatever's at the center of it the temperature that it is for a longer time, right? It keeps heat from flowing in or out. That's that's why whales have blubber, right? And so fat is definitely an ingredient or a component of our ingredients that we have to consider when we are designing what our thermal processing looks like. So then our third and fourth aspects of food components that we need to consider are particle size and density. And so for both of these, the larger the particles are, or the denser the ingredients, the more the product must rely on conduction. It's like I was telling you with, a beef stew. When you have those particles, well, the convection is happening in the liquid, but once it gets to the heat gets to that particle, it's conduction going into the particle. And so conduction is slower than convection. So Then with density, the denser it is, the less convection is going to happen, the more it must rely on conduction. So a heavy sugar syrup is more dense than light sugar syrup, like if you're talking about a fruit cocktail. Products that are thickened with starches are going to be more dense and take more time to heat through. There are some starches that don't thicken until they're cooled, and so those could use more convection, but having a knowledge of your products is important. So my examples for particle size versus SpaghettiOs, I have this beef stew which has big particles. SpaghettiOs are a lot smaller. So this beef stew will rely more on conduction, whereas the SpaghettiOs will rely more on convection. Here I have sweetened condensed milk versus evaporated milk. And so if you've ever noticed the difference between the two, that sweetened condensed milk, it is dense, okay? When you are pouring it, it is super viscous. You can see that with this example with the spoon here, versus evaporated milk. It's maybe a little bit denser than regular milk, but it pours easily, okay? You can pour that right out of the can and it will all come out within a few seconds. And then it shows this, very much less viscous stream of liquid coming off of the spoon in this picture. So this sweetened condensed milk is going to require higher heat to get that completely sterilized, commercially sterilized, versus the evaporated milk. Okay, and finally, the last factor to consider in heat processing when determining our methods and our time and temperatures, etc., is the pH of the food. And we've already hit on this a little bit, but high acid foods, which have a pH of less than 4.6, they can be heat processed at 100 degrees Celsius, so boiling temperature, because Clostridium botulinum does not grow at that low pH. But those low acid foods where Clostridium botulinum can grow, we have to get those to higher temperatures in order to kill those Clostridium botulinum spores. So, kind of summarizing what I've said a couple times, the three main points that we need to consider in commercial heat processing are food safety, first and foremost, followed by food quality and cost. And it is just a balance of all three of those in determining what type of heat processing method we're going to use, what the time and temperature combination that we're going to use is, and yeah. So then, considering all those points, now we're going to decide exactly what heat processing method we are going to use. Okay, and those two categories, and here we're really focusing on the commercial sterilization portion of this with this point. So those two categories are heating after it is packaged or heating before it is packaged. And the advantage of heating before it's packaged, if you choose to do that, is that you can minimize the processing times to cause less damage because you're only heating that food. And I take that back. We're not just covering commercial sterilization. We're going to cover pasteurization too. But okay, so heating food after packaging. So there are two main methods here for heating food after packaging. And the first one is retort. A retort is a large commercial pressure canner. So these are big tanks that fit lots of cans stacked in them. The door will be closed, will be filled with water. It's heated, pressure builds up, and you're able to heat it to the 121 degrees Celsius that is required to kill spores, to kill botulinum spores. Now, you can do this with or without agitation, but agitation does reduce processing time. So if you're agitating that water in the cans inside the retort, it does reduce the processing times. You're also able to use higher temperatures because if the cans are still, then you're having constant high heat on the sides of those cans, and you can get burning to the sides of the cans. But with the agitation, and with the cans being agitated, the liquid inside it is being agitated as well, and you reduce the amount of time that any one particle is up against the side of the can and prevent burning and sticking to the sides there. And so overall, it can result in faster heating and more uniform heat distribution. The second method that we can use to heat food after we've packaged it, and so we're still talking about in a can here, is the hydrostatic cooker and cooler. So the processing times, like the heat temperature time combination, is similar to an agitating retort. And what's different about these is instead of it being a big batch that goes into a tank, it is on a conveyor belt system. And so these cans are on a conveyor belt that they're going through here. It's preheated. They go through a sterilization part where the pressure is high also, so that it's still getting the high pressure temperatures here. And then it goes continuing on its little conveyor belt into a cooling area. And so it's able to be heated and cooled really quickly. Okay. So there's some advantages for quality there because it is able to be cooled more quickly. And so there's less time that the food inside is warm. And the other advantage is that it actually has a higher throughput. You're able to get more cans through this in a shorter amount of time than with a batch retort, because you think about a batch retort, you have to load all the cans onto the whatever mechanism that you're getting it into the tank. Then you have to close the tank. Then you have to refill it with water. That water has to be heated and pressurized enough to a point where it gets them enough to a point where it can complete that commercial sterilization. Then you have to empty that water, refill it with cold water, and then empty it again, take it all out, right? Whereas this is just a constant process. You're not having to have those steps where you are filling with water and heating and building up pressure, releasing pressure, and also the just getting in and out of the cans. And so able to, with a continuous process, get more done. So so that was heating foods after packaging, and now we'll talk about heating foods before packaging. Okay, so the first method here is one of our pasteurization methods. Okay, it's batch pasteurization, and I think we've talked about this before, but it's the oldest method of heating prior to packaging. Right, you just have usually a liquid in a vat, and you slowly get it to the temperature that it needs to be to pasteurize it, and then it would be pumped out over a cooling plate and packaged and sealed. This isn't done very much anymore because now we have better systems that heat and cool very quickly. So the second method of heating food before packaging is called high temperature short time, or HTST. And it's also pasteurization. And so the milk comes in raw from the storage tanks. It is pumped through smaller piping, and that piping is jacketed in high heat. So it's going to go through a high heat area of the piping, and then as soon as it gets to this high temperature for a very short time, it's then going to go into piping that is jacketed in cold temperatures to cool it down quickly. And so the milk is exposed to the high temperatures for as short of a time as possible to achieve that pasteurization, and it causes less damage to the enzymes and flavors and things in the milk. And this is not just for milk. Juices and things use this too. Okay, the third method of heating food before packaging, and the last one that we'll talk about, is aseptic packaging. And the book calls it aseptic canning. I prefer the term aseptic packaging. That's used more often. And in fact, the book almost kind of slips up in one little part and does call it aseptic packaging. And so that's the term that I'm going to use, is aseptic packaging. So aseptic means free of pathogens, okay? And this food, it can be preserved to commercial sterilization or even to the full sterilization level using this. So it can be either or. Most often the stuff that you buy at home is going to be commercially sterilized and not fully sterilized. And so what happens with this, the food is cooked to a commercially sterilized temperature in a very sterile environment, and then it is put into sterile packaging in also a very sterile environment. So sterile means free from any microorganisms, right? And so that's how it's packaged. And so even though it wasn't cooked at all after it was put in the package, it is commercially sterile, or so that it can be stored at room temperature. Okay, this is often called UHT, which stands for ultra high temperature. So the temperature that is being achieved on these products is even higher than that high temperature short time that is used in that pasteurization. Okay, so if you've ever seen these milks, these are UHT milks. You'll often see UHT milk sold by fast food restaurants, and you can look on the packaging and it'll tell you whether it's gone through ultra high temperature pasteurization. It'll say that it will not say that you have to keep refrigerated, and so that's one way you will know. Other products that go through UHT sterilization, so like protein drinks, right? If they're not canned, if they're in like a plastic packaging, for sure they've gone through this. The little pouches that have whatever kind of food in them, be it tuna or chicken or like stir-fry sauce, these have most likely gone through this. There's another form of pasteurization that we'll go over in a minute that is possibly what some of these have gone through, but most likely, especially the tuna, is usually UHT. Okay, you have any product like stews and stuff stored at room temperature on the shelf that are also not in a can? They've gone through this aseptic packaging also. So now let's talk about home canning, because this is going to be the one that's probably more applicable to you unless you do decide to go into the food industry. What should you consider if you're canning at home? So the basic home canning steps are, clean your jars, make your recipe, fill your jars, which is also called packing your food, and then processing the cans or the jars. And so I'm going to focus here on the packing the food and the processing the cans steps. So there's two ways that we can pack the food. The first is cold pack. So in this type of packing the food, you put it in your sterilized jars without heating the food. Okay, you just put those raw peaches directly in. And then you pour boiling water or syrup over the food. This is most recommended for foods that are easily damaged. So, peaches is the example the book uses. Also, pickles or tomatoes that are uncooked that you want them to keep that uncooked consistency. Anything that you're trying to retain the crunch of it. Uh, Also, potatoes, right? Potatoes soften really easily if they're heated too much. Uh, Also, anything that's going to go into a pressure canner is often cold packed, mostly just for the ease of doing it. Because if you're hot packing, on the other hand, well, these foods you're going to be uh, heating in the syrup or juice or water prior to the packaging. So it's an extra step. Um, and you're going to hot pack foods that would be diluted if you were to add boiling water, like peaches, right? Uh, Now, an advantage of hot packing, you can use it as an advantage, is that it softens foods. It also expels air bubbles from the foods, and so it allows tighter packing and 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 can affect the quality. So in this picture here, it's showing you hot packed and raw packed or cold packed peaches. And you can see the peaches have floated to the top. Because they were cold packed, there was no expelling of the air bubbles that were in the peaches, and so they'll float to the top. And that will actually lead to a shorter shelf life. Also, some of that air will eventually escape the food product, and you'll end up with a bigger airspace, headspace at the top of the jar. And again, that will lead to a shorter shelf life. So advantages and disadvantages of both. So once that food has been packed into the cans, you still need to process the cans to get those foods to a good temperature that is going to commercially sterilize the foods. So two methods are water bath processing and pressure processing. And how you're going to choose those is the pH level of that food. So your high acid foods that are pH under 4.6, you are just going to be able to seal those containers in or submerge those sealed containers in boiling water. And so you just have them in the boiling water for a certain amount of time based on the food and the size of your jar, etc. And it's as easy as that. And so those high pressure foods include things like fruits, pickles, tomatoes. But if your pH is at or above 4.6, those are considered low acid foods, and you're going to have to do something to destroy the Clostridium botulinum spores, which means that you're going to need to use a pressure canner to get that temperature up to higher than boiling temperatures, and heating those foods under pressure to do that. And so foods that will need that pressure processing include most of your vegetables and as well as meats. Okay, and then what I'm going to add to this chapter, and I expect you to know this is not just bonus, okay, are two methods of pasteurization that are actually not thermal methods at all. Temperature has nothing to do with them, but they're called cold pasteurization, and that's just because no heat is required, okay? So typically the foods are being kept cold while they're doing it. So the first one is high pressure processing, and also known as just HPP. And with this one, it is purely pressure that is destroying the microorganisms. The pressure is so high that it inactivates the microorganisms as well as enzymes. So the food enters this tank, there's water pumped into it, and then it is held at this very high pressure. Here says up to 87,000 psi, and that inactivates the microorganisms. Now, the one detriment to this is that it is ineffective against spores. So It because of that, it's generally limited to refrigerated foods. You're not going to achieve sterilization with this at all. And so the HPP product comes out and refrigerate it, and it has a longer shelf life than other similar refrigerated products. It keeps most of its quality because you haven't done that thermal processing. So some examples of high pressure processed foods. So like the refrigerated, like individual juices, like the Awala, or what is that one brand? I'm drawing a blank. The juices that are like in the produce section of the store, those are high pressure processed. Um, Also avocados, if you buy the avocado that is, or guacamole that is refrigerated and packaged already, so not like whole avocados, but the packaged stuff, it actually has had high pressure processing done, and it's not so much for the pasteurization aspect, although that's great. But the really great thing for that is that it inactivates the enzymes that cause browning in avocados. And so that avocado product does not brown, which is helpful. There are lots of other ones that I can't even think of right now, but this is a growing a growing thing in the industry. It is expensive because it's in batches. There's not a continuous way to do this currently, and the tanks are like huge, and so you have to load this huge tank and then do the batch and unload it, uh, and it's a little bit cost prohibitive, but uh, but yeah, it's a good technology because you're able to do some preservation without having as many preservatives and chemicals on the label. Okay, and then the second one, which we might get into later in the book, I don't remember, but we're still going to go over it today, is irradiation. So irradiation, no heat required. There's just ionizing radiation that is used to kill pathogens, spoilage organisms, and insects, depending on the dose. So you can have a low dose that really just kills insects, or you can have a high dose that makes the food completely sterile. It can also be used to inhibit sprouting and delay ripening. So um, it's not really commercially used for the retail today, but there's studies and things that I've seen that with strawberries, they can make strawberries last much, much longer because they irradiate them, it delays ripening, and it also kills any mold and things that are naturally on the strawberries, and so the shelf life is increased by a lot. Um, Bad things about it, it can increase oxidation of food. So specifically foods that are high fat, right, which are more susceptible to oxidation. So it can affect flavor in that way. But otherwise, it is very, very safe. But unfortunately, uh, because it hasn't taken off, it's probably part of why it is very cost prohibitive. Uh, and so there is a high cost to it, but probably what has caused the high cost is, the the more you make something, the lower you can make the cost, right? But it hasn't been used much at all, mostly because of consumer wariness. People see irradiation and are like, no, and so nobody has really been brave enough to try to put this into the retail market. It's been around forever, since the 1950s, and has been approved for a long time as well, to be used on lots of different products. So in the US, any first generation products must be labeled. So if you are buying raw spices or raw fruits or a meat product, right? If that product was irradiated, it has to be labeled, and it'll have this symbol here that's called the Radura symbol, and that denotes that it's been irradiated. Now, if it's not first generation, if it is just used as not the main ingredient, but like an ingredient in a food, then it actually does not have to be labeled. So for example, a spice that is used as a component of something else, it does not have to be labeled that with the Reduro symbol on that bigger product. So actually the most common irradiated food in the US is commercial spices. And that's exactly how it's used. They're irradiated before they get to a further processor, and the further processor is adding those spices to whatever food that they are making, and then they don't have to label that. And it is a good thing that they are irradiating commercial spices, because it does reduce pathogens in those spices, and spices can be a major source of pathogens in food. But I will say the ones that you get at the grocery store, they're not irradiated, because nobody wants to take that first step and have to put this symbol on foods that they are selling to consumers right now. So, okay, and so that is all that we're going to cover for this chapter. You're going to completely skip the cold processing unless you just want to read it for fun, but it will not be on the exam. Oh. All right, so y'all have a good week.